Most amusement parks have a hall of mirrors, a traditional attraction. Mirrors in these halls are often distorted into different curved, convex or concave shapes to give the participants unusual and confusing reflections of themselves. They may see stretched, shrunken or even bloated forms of their images. Sometimes the images are startling and at other times hilariously funny. Thus, the Hall of Mirrors can use properties of spherical mirrors to create an unusually funny experience for visitors. Of course, that's not the only area where spherical mirrors are used. You may be using spherical mirrors in your everyday life without being aware of it. In this lesson, you will learn about types of spherical mirrors and their uses. At the end of this lesson, you will be able to describe spherical mirrors, identify the characteristics of images formed by a convex mirror and concave mirror, and apply the mirror formula and sign convention to find out the relationship between distance of object and image from a mirror. A spherical mirror is made from a part of a hollow sphere of glass. In other words, it is a plain glass bulging inwards or outwards. Spherical mirrors are further classified as convex and concave mirrors. A convex mirror reflects light from its outer spherical surface and has a silver coating on its inner surface. Convex mirrors are usually used as rear-view mirrors in automobiles. A concave mirror reflects light from its inner spherical surface and has a silver coating on its outer surface. Dentists usually use concave mirrors to examine teeth. You need to be familiar with the terminology used in calculations involving spherical mirrors before you get into more detail. Let's start with the center of curvature. Center of curvature, C, is the center of the sphere of which the mirror is a part. Radius of curvature, R, is the radius of the sphere of which the mirror is a part. Pole, P, is the geometric center of the spherical mirror. Aperture is the surface of the mirror used for reflection. Principal axis is the line joining the pole and the center of curvature. Principal focus, F, is a point on the principal axis. This is the point where the rays in the reflected beam formed from the incident beam parallel to the principal axis converge. Focal length F is the distance of the principal focus from the pole of the mirror. Objects seen in the mirror are closer than they appear. You may have seen this warning sticker on the rear-view mirrors in your cars and bikes. These rear-view mirrors are actually convex mirrors. Rear-view mirrors help the driver to keep an eye on a large area behind the vehicle by providing a wide field of view. The behavior of the light rays reflected from a convex mirror varies based on the angle of incidence on the mirror. Let's take a look at a few cases of reflection of a light ray from a convex mirror, taking the example of a rear-view mirror. In the first case, incident rays are parallel to the principal axis. In this situation, the reflected rays appear to pass through the focus. In a rear-view mirror, incident rays parallel to the principal axis enables the driver to see the car traveling exactly behind this car. In the second case, let us consider incident rays directed towards the center of curvature. Here, the angle of incidence is 0. Hence, the angle of reflection too is 0. Thus, the reflected rays retrace the path of the incident rays and appear to pass through the center of curvature. This enables the driver to see the parking meter on the other side of the road. Next, look at incident rays that are directed towards the principal focus. The reflected rays go parallel to the principal axis. This is how the driver is able to see the traffic signal which the car has crossed. Finally, if incident rays strike the pole at an angle with the principal axis, the reflected rays also make the same angle with the principal axis. This helps the drivers of two cars traveling alongside to look at each other in the rear-view mirror of the car ahead. In concave mirrors, such as a dentist's reflector, the reflection of rays is somewhat different from that in convex mirrors. Concave mirrors help enlarge the images of faraway objects or view objects that you cannot directly see due to their position. As in convex mirrors, reflection of rays in concave mirrors also follows certain rules. If the incident ray is parallel to the principal axis, the reflected ray passes through the focus. If the incident ray passes through the center of curvature, the reflected ray retraces the path of the incident ray. If the incident ray passes through the principal focus, the reflected ray goes parallel to the principal axis. If the incident ray strikes the pole at an angle with the principal axis, the reflected ray also makes the same angle. The focal length of a spherical mirror depends on its radius of curvature. Consider a ray Q parallel to the principal axis incident at point M on the mirror. This incident ray is reflected in accordance with the laws of reflection. When the reflected ray is extended beyond the mirror, it meets the principal axis at point F, which is the principal focus of the mirror. We know that angle I is equal to angle R by the laws of reflection. Angle I is also equal to angle MCF, as they are corresponding angles. Additionally, angle R is equal to angle CMF, as they are vertically opposite angles. Therefore, angle MCF is equal to angle CMF. Therefore, CF is equal to MF. If point M is very close to point P, that is, the linear aperture of the mirrors is very small, then MF is equal to PF. Therefore, CF is equal to PF. Also, PC is equal to PF plus CF, or PC is equal to 2PF, since CF is equal to PF. Therefore, R, the radius of curvature of the spherical mirror, is equal to 2PF. But PF is nothing but the focal length of the mirror. Therefore, R is equal to 2F, or F is equal to R divided by 2. Hence, in case of spherical mirrors, the focal length is half the radius of the curvature. When a beam parallel to the principal axis is incident on a convex mirror, its rays diverge. These rays, when produced backwards, appear to diverge from a point known as the principal focus. The image formed by a convex mirror is always erect, virtual, and diminished in size. The location of the object does not affect the characteristics of the image. Thus, as the object approaches the mirror, the image approaches the mirror too, but not proportionately. This is why the rear-view mirrors of cars and bikes are made of convex mirrors. When a beam of rays parallel to the principal axis is incident on the reflecting surface of a concave mirror, its rays all converge at a point on the principal axis. This point is known as the principal focus of concave mirror. Unlike a convex mirror, the nature and size of the image in a concave mirror depends on the relative position of the object from the mirror. Let us examine the characteristics of the image of an object at different points in front of the mirror. When the object is at an infinite distance, the image is formed at the principal focus f. This image is real, inverted and highly diminished in size. When the object is placed at a finite distance greater than the radius of curvature r, the image is formed between the principal focus f and center of curvature c. This image is real, inverted and diminished in size. When the object is placed at center of curvature c, the image is formed at the same point, that is, at c. This image is real, inverted and equal in size to that of the object. When the object is placed between the principal focus f and the center of curvature c, the image is formed beyond the center of curvature c. The image in this case is real, inverted and magnified. When the object is placed at the principal focus f, the image is formed at infinity. This image is real, inverted and highly magnified. When the object is placed between the principal focus f and the pole P, the image is formed on the side of the mirror that is opposite to the object. The nature of this image is virtual, erect and magnified. Now, based on your knowledge of spherical mirrors, let's examine how these mirrors are used in amusement parks. The hall of mirrors that you saw earlier uses combinations of concave and convex mirrors to show funny, distorted images to the viewer. Concave mirrors are converging mirrors. They help us view enlarged images. Therefore, if you stand close to such a mirror, you will see a wider, fatter image of yourself. On the other hand, standing close to a convex mirror will make you appear thinner. With a set of such mirrors around you, you can see a variety of images of yourself, an undoubtedly interesting experience. The analysis of properties of images formed in convex and concave mirrors showed us that these mirrors present images that are either smaller or larger than the relevant objects. The ratio of the height of the image in a spherical mirror to the height of the object is called linear magnification. Linear magnification is denoted by small letter m. You can determine the size of the image reflected in a spherical mirror by using linear magnification. You can also compute magnification as the ratio of image distance to object distance. Thus, the ratio of the height of the image to the height of the object is equal to the ratio of image distance to object distance. Magnification can be unity, greater than 1, or lesser than 1. Magnification is unity when the size of the image is equal to the size of the object. When you look at your image in a plane mirror, it is of the same size as yours. Therefore, the magnification of plane mirror is unity. In other words, there is no magnification. Magnification is greater than 1 when the size of the image is greater than the size of the object. When the object lies between C and F of a concave mirror, the image formed is inverted, real and bigger in size compared to that of the object. In this case, the image is said to be magnified. Thus, magnification is greater than 1. If the object is placed between F and P of a concave mirror, then the image formed is virtual, erect and bigger than that of the object. Hence, in this case also, the magnification is greater than 1. Dentists use this situation to view the inner parts of a mouth with more clarity. Magnification is lesser than 1 when the size of the image is lesser than the size of the object. When an object is placed beyond C of a concave mirror, The image formed lies between C and F of the mirror. It is inverted, real, and the size of the image is lesser than that of the object. Thus we say that the image is diminished and its magnification is lesser than 1. In the case of convex mirror, irrespective of the position of the object, the image formed is virtual, erect, and its size is smaller than that of the object. Hence, in a convex mirror, the image formed is always diminished and its magnification is lesser than 1.